Day 4, I will cover delay TCO, how to run Vivado in VScode. I will show how RAM work, including DRAM and SRAM, and lastly, a plan for the next day. Yesterday we talked about MUX, that is bridging the input to the output by changing or by setting the selection pin here. And the same thing with the MUX, we can bridge the input to different output by setting the input selection. Now, an interesting topic, how can we create a delay using digital blocks? As you remember on day 3, we learned how the flip-flop work. So basically, it's based on either rising edge or falling edge. If we have an input here and there's a rising edge, then the output gonna be matched with the input. For example, right here, at the first rising edge, we have D equal 1, which input equal 1, so output equal 1 here. And then the next cycle, the rising edge is 1, D also 1, so the output is 1. But then for the third rising edge, the input is 0. So at the third rising edge, the output is also 0. And that is how the flip-flop works. So we can use that mechanism for a delay. In this example, we want to delay 2 clock cycle, and we're gonna send this string of bit or just a hex to this series of D flip-flop to see how it works. And QC is the final output. We have 1 there. And then in the first cycle, QC gonna be X, which is unknown because assuming we don't have any value before it. And in next cycle, the input of 1 gonna be the output of the other, so it should move across all the flip-flop there. And as you see, after 2 cycle, the value of QC is 1, so it's delayed 2 clock cycle. And on your right hand side is the Verilog code. So first we define the signal wire, and then we also define 3 different register or the flip-flop we call it R shift. So we're gonna shift the register 1 to value of register 1 to value of register 2. So this is 0, this is 1, and this is 2. So we shift the value of register 1 to register 2, 0 to 1, and shift the input to 0. And we also assign this value to the output data, which is QC. So that is how it works. I also realized we can run Vivado in VScode. There's different mode. There's GUI mode and there's also patch mode. We can run patch mode, but first we need to run this patch file to add all the binary or executable files into the path. And I just realized we need to call this script every time we open a new terminal. So one way to make it easier is to add the path of the patch file into terminal profile of VScode. You can press Ctrl B and go to the setting and search for this, and then it will direct you to the JSON file that you can edit it. PowerShell is a default terminal in VS Code, but you can also change to command prompt. This is quite interesting. So in VS Code, you can create a folder that include a design code and then a test code, man_tb test bench, and also a TCL script for simulation. So I think the TCL here is like a patch file or like a make file or YAML, something like that. And if you successfully run the TCL file, then you see these in the terminal, and it's going to create this file inside a dedicated folder that we set in the TCL. Let's see how each block works. So for the main code, I just write a simple series of D flip-flop for delay. This is a test code. And next is the TCL for simulation. And finally, it's going to generate this file. And you can actually click on this project file to see the wave as I show here. So the problem that I show is this one. So as you see here, the input is about 15 nanosecond, but the output is more than 15 nanosecond. I think this is 20 nanosecond. So the reason of it is because similar to the first problem with 2 clock cycle that we have, because we start at like a random point, the input data is asynchronous with the clock. So that is the case, and here is the table that I analyzed it, why it happened, and the code is fine. So here I show the previous example where the duration of this signal is shorter than the output. So similar issue. I think we can apply synchronous for it to improve it. Alright, so just move forward. There are 2 types of RAM, random access memory and cache, which use static RAM. Main memory is DRAM, dynamic RAM, and virtual memory is hard disk. So RAM is based on latch. Latch is the thing that you see in SR latch that you inverter connect back to each other, and I think that's they use transistor to set the charge. Unlike SRAM that use transistor and resistor, DRAM use just capacitor and transistor, mainly capacitor to store a bit, because there's a leakage in capacitor, so it have to be refreshed, and also reading erase the bit stored in the cap, so it also need to restore the bit every time it read the value from DRAM. That is the reason DRAM is slower compared to SRAM. So we talk about flip-flop, we also go over RAM. For RAM, sometimes you see block RAM like 16A or something similar. So that's the width and depth of the RAM. Basically, this is a functional diagram of RAM. Data in here, right here is a clock to enable writing, address to set where to store the data and data out. So A1 here is the width is A, so it can store 8 bit. 1 here is just like 1 bit, and if you have like A multiply A, then it can actually store 8 byte. If we increase the depth of it, like A times A, then it can store 64 bit. In our case here, A times 3, it can store 24 bit. And a detailed functional block of RAM, there's a 2-port RAM where you can write and read it can use different clock here. For reading, you can apply a clock cycle, the address, and a port to write each data. Same thing with read, and you also need to apply a cycle, a clock cycle, the read address to read, and read enable. We need to apply high signal here to read. That's it. In day 5, I think we might cover architecture of computer, and that's all. Thank you.